I'm going to get rid of that. Okay, so it's a pleasure to have Chun-Yu Max Lin from the Institute of Computer Science, Czech Academy of Sciences, Department of Logic, Faculty and Arts at Charles University, come and talk to us about non-classical polyadic algebras, soft and hard. Please, Max.
Yes, thank you very much, Peter, and thank you for the audience here. So today I'm gonna talk about some small discovery, not a very big one, of course, about classical polyadic algebras and soft and hard. I will explain what does it mean soft and hard, but it's not my own interpretation. It's actually from Hong's famous textbook, that Abstract Algebraic Logic. And he introduced like soft and hard about interpretation of or semantics of algebraization of like predicate logic. So he used this terminology inside his textbook. So I will try to control my talk between 45 and 15 minutes so that we can leave most of the time discussions and brainstorming. And yeah, I would like to know more about it. Yeah. So this is the outline of the talk that I'm gonna give today. And yeah, so and in the end, I can just give you a one sentence summary about the main point of today's talk at the very end of today's talk. Yeah. So I'll go into some settings, and of course we will introduce briefly about the classical polyadic algebras. I will use Halmos framework, which is somehow outdated for some experts because we have more modern understanding of polyadic algebras recently. But I will explain why I use this framework, and then later we'll move on to non-classical polyadic algebras, and then I will explain how they connected with algebraically implicated logics, and then the main thing is about the representation theorems. And I guess this is a pure algebraic result, and it's also an important result that Halmos mentioned inside his paper. And also in the end, I will talk about there are more works to be done. So James Fong's explained inside his textbook, it's actually the very end of this second chapters about how could you do algebraization of predicate logic or first order logic in a abstract algebraic logic perspective. And he said if we associate a class of algebra with the logic, and so the algebra should have similar types with the language of that logic. So thus, in this perspective, the algebraic formulation of predicate logic as cylindric or polyadic algebra is closer to the spirit of abstract algebraic logic, rather than interpret the quantifier as an infinite join on bit. So he called if you evaluate quantifiers as infinite lattice operations, he called it some kind of layer, because you are way between the actual semantics and then the syntax. So you use the syntax you have for the logic, but you are not really interpreting the quantifier. And the second one is he called it hard way. The hard way means we evaluate quantifier as an independent, as a unary, primitive operations. So we don't use other logical operation to interpret our quantifier. We take the quantifier as a primitive part of algebra, but it makes things more difficult. And I think 60 or 70 years ago, a lot of logicians and algebraists started this kind of work. And then, of course, there are a lot of work inside this direction. So there's a naive question that can we find a connection between the soft and hard interpretations of quantifiers? And the answer is yes. And it somehow hidden inside a some kind of less well-known paper by Don Gozzi and Antonio Salibra, if I pronounce the name correctly. So they actually build a connection between, use our modern terminology, we call it Rasiowa, implicative logic, and then the Polyadic algebra. And they also prove the representation theorems inside their papers. So this paper is actually not that well known, and then it depends on their previous work about binding calculus within using binding calculus to study the algebraization of predicate logic. So then, all right. So, and today's talk, actually, if you really dig into that papers, you use a principle and then you use our modern understanding of like implicational algebraic logic, then actually you can push the restriction a little bit and try to generalize it. And that's why I talk about like algebraically implicative logic. So if I want to give a one sentence about today's, like one sentence summary about today's talk, then I will just tell you that actually their results can be generalized to algebraically implicative logic. And in the following slides, I will tell you how to do it. But if you know what happens inside the paper, then that's not difficult. And then you just have to put everything in the right direction and you get the thing you want. So here's the setting, and so here's the setting, and now we're gonna introduce what happens inside classical Polyadic algebra. And of course, if you want to algebraize predicate logic through Hamel's approach, then besides the logical part, which you might use Boolean algebra to algebraize the propositional part, but you also need to take the quantifier as an independent operators. And the only things which is extra is about substitution. So, and substitution is I would say it's a key idea which separates cylindric algebra and then Polyadic algebra apart. So I'll mention briefly in the end. So I already know the identity transformation by this kind of alpha. And also this is some kind of standard notation happened inside Hamel's paper. So we say two transformation, we say they are equal like we use this notation sigma j tau means they are equal on the set of j, and we don't care what happens outside like j. And also if we really care like what happens outside j, and then we don't care about what happens inside j, then we'll use a complement notation. So sometimes Hamel's himself inside the paper, we're gonna somehow assume that you are familiar with the manipulation of this like notation. So, and if we write like sigma j star alpha, then we say j supports like sigma. That means okay, how to say, like j is the thing that really control, and then everything outside of it I will just map, or I'll just keep it and don't move it. That's the like intuitive explanation of this notation. And of course we try to formalize first order logic. So I will use the standard notation. I will have like set of propositional connectives, and then these kind of phi is a set of generalized quantifiers. And actually inside their paper, they provide a quite general framework about how to algebra the first order logic, and P P and F will be some like relation of function symbol, bar will be set of variables, and then because we need to study the arity, so we have to grow to know the arity of like function symbols. Yeah, so this is some basic setting. Yes, so for quantum fire, this is from like 1950s. I think he has some paper like earlier than this, but I just cite his like algebra logic 2 papers, which appears in like transactions of American Mathematical Society or somewhere. So the classical Polyadic algebra, inside it, we need to first define what is a quantifier, and then an extensional quantifier and Boolean algebra say it's a mapping that you just send button to a button. That means you quantify with button, then nothing happens. And because if you think about it, then the soft approach would help you to understand the second definition, because usually we would say extensional quantifier would be interpreted as a supremum of some set. So that means extensional quantifier will be some kind of monotonic unary functions, then P will be less than to P. And the third thing is once you quantify something and you quantified it again, then it wouldn't change anything. So that is based on his understanding of pedagogic logic around that time, he wrote down these 3 definitions. And here's a list, like actually using our like modern terminology, we'll call it quasi-polyadic algebra. Then there are a lot of like different families of polyadic algebras nowadays. So, but I'll use his own like definition. So a quasi-polyadic algebra will say you have a Boolean algebra which interprets the classical propositional part of logic, but we need a set of variables, the I, and quantify, because we might quantify it on a set of variables. So actually quantify operation would be a mapping from subset of variables to the actual quantifier defined in the previous slides. So that's the classical definition. And then the final part is that I think this is the most important contribution of this approach, is like how could you formulate substitution in an algebraic way. So the first 2 is about how to like find actual quantifier in this setting, and then it's quite straightforward. And the following definition is to characterize what happens within substitution, and then the interaction between if you quantify something first and then you do the substitution, then what happens. And so here is like, if you read his like series of paper, he actually provides some interpretation or explanation is a more correct word about how to read like the following 4 different definitions. So the first thing is if you do nothing about substitution, then actually there's nothing happens, because your transformation is an identity transformation. So you do not do any substitution. In the end, nothing will happen.
So, but in that axiom, the I sub 1 sub I is the identity function, is that right?
Yes.
And then 1 sub A is the top element of the Boolean algebra. Or is it?
It's an identity morphism, and it's an endomorphism. So it's actually yes.
Okay.
And this is like more than presentation of like substitution, because inside his paper he writes something very like hand waving way.
Okay.
But if we have like general understanding about algebra, then you can easily write substitution in this way, and that's I think recently people gonna write in this way. Yeah, and if you do substitution sequentially, then actually you can. This is the second one. If you apply substitution of the variable, like you first do tau, then you do sigma, then you substitute something first, then you do sigma second times, then that will be the same thing. And yeah, it's a kind of tautology, but
Can I ask something?
yes.
Is there any reason why they privilege the existential quantifier in relation to Bose quantifiers? Or could they do
Actually,
the same thing or not?
if you read his papers, previously he would use, at the very beginning, he used universal quantifier in his very first paper, published on American Mathematical Monthly. But in his more formal or mathematical paper, he used essential quantifier, and of course, classically it's interdefinable. So, but he didn't. He doesn't explain inside the paper why he changed from universal quantifier to essential quantifier.
Possibly because it's easier to work with this judge.
Yes, I think so. I think so.
Yeah.
So if you read his more applicational paper, he used universal quantifier actually. So I don't know why he changed his changes his mind. And yes, and the third thing is if you once a variable has been quantified, and then the replacement of that quantifier by another one actually has no further effect. And you should see this, because if you, if you take J to be, let me see, not J. If you take tau to be some kind of identity transformation, then that means you doesn't move anything here. So this is the identity. Then you'll have S sigma exit J means exit J. And this is the examples that Halmos write inside the paper. So that means if you quantify something, that the replacement of that variable by other one actually doesn't change anything. Yeah. And the fourth one is if you quantify some variable which has been replaced by other thing, and then because the variable has been changed, so you quantify the non-exist variable, then nothing will happen. That's the understanding of the fourth definitions. And if you pick into this definition, and yes, you will realize that actually, if the definition somehow, the definition don't really rely on the structure of Boolean algebra. So this is how the framework right now I will present is based on Pigozzi's 1993 papers. So I don't do any new works on this. So he realized that actually if you change the Boolean algebra from Boolean algebra to a more general algebra, you can rewrite everything in the same way. So if you see what happens here, then you will realize that actually all the axiom here is actually you just rewrite everything, and then the definition still works. So I think that is observation. So but I here I changed the notation a little bit to separate from the classical, to separate between classical and non-classical case. Yeah, but if you pick a little bit about what happens here, then the patterns is actually the same. And the definition doesn't restrict to the arity of the logical connectives you can use. So you will have more general definitions. But once you propose a definition, then you would like to see then what happens in functional polyadic algebra side? But why functional polyadic algebra is important? Inside Hammond's paper, you will realize that that's the only examples he can figure out during like his study. So why he wants to study functional polyadic algebra, because that's the only things besides writing these axioms, then we would like to see some real examples. And then, but I think he spent a lot of time and then tried to see what's the examples, and in the end we realized that okay, actually functional polyadic algebra around his time is the only examples he can find.
What do you mean by functional?
A functional means right now our domain, I will explain later in the slides.
Okay.
So and functional polyadic algebra means our domain right now would be a set of functions. Then we need to define, for example, what's the operation on the functions, and how could you quantify all the functions, and then what's a substitution on the function, because your domain will be a set of functions. So classically, he also does this inside his papers, and then it will make things more complicated, of course. That's right. Your domain is out.
And the non-classical means you can have any
Yes.
any operations. I mean, connectives. The connectives can be arbitrary. They don't have to be a Boolean algebra. They don't.
Yes, they can be arbitrary. That's
They
what
can be
happens.
just
Yes,
arbitrary.
that's what happens inside, because it's paper that he doesn't restrict to anything. So he provides a quite general framework, and that like around second part of the paper, he gives you how to use this framework to study residual or implicative logic. But around that time, we don't have like full understanding of about what happening inside the implicative family of like abstract algebra logic. Of course, right now nowadays we have like better understanding about these families of logic. So that's why I give a talk today to tell you. And I think that's the like limitation of this framework if you want to study the implicative family of like abstract algebra logic. Yes, and I will. So to do like functional polyadic algebras, then first you need to define what's the value algebra. And of course, classically, you just like put in algebra, of course. But here it's like first a value algebra is actually we just take a domain arbitrary set, and the different things is your quantifier is actually a partial unary second order operation. So you quantify, here is a set of B, but it's a partial. So that means you quantify something that might be undefined or they might be defined. Yes. So because right now we might enter into some details, and then might try to be somehow try to explain what happens inside it and not dig into the explicit detail about it. And so then what else you need to define is the function. You take the function here, and then these things means I have like propositional function which evaluate in a classical way. So we have a set of functions with index like variable here, and the operations you just change the domain, so the operation is the same thing you can define. And here your quantification will be, if you see what happens here, you just change your domain here. So the quantification here means you will have QV. I abuse a little bit about the notation. So you have, once you choose a subset of variable, then you will have like quantifier, actual quantifier here. So if you review a little bit what happens inside classical case, actually this is an endomorphism of the Boolean algebra. But I just change a little bit and to use the like more function style notations. And the definition here actually it's not quite new. If you see what happens within the classical case, it's still a total rewritten everything. So there's like not something very creative inside these things. So you just say, I want to do in a non-classical way, but I just follow the patterns and follow all the definition happens in the classical sense. Yes. So that's the definition of quantifier in the substitution here. And of course, because we study partial functions, so we want to avoid some kind of difficulties happen beside it. So we try to restrict to a total function, which somehow makes things easier or make your life easier, I would say. Then if you make a restriction and say, I just want to study like what happens inside total function, actually inside a paper, you can actually prove that, you can really prove that every functional Polyadic algebra is actually Polyadic algebra in a non-classical sense. So to prove these things, there's nothing to do but run through all the like check, because this is the automatic definition of non-classical Polyadic algebra. And then the functional one, you actually give me the definition quantified this way. Then the only thing is you have to do is to step by step to see actually the thing you defined really satisfies the equation you have written down. So there's nothing. But for the converse, as the classical case, like our papers, things not always happen. So we need to make some restrictions, as almost mentioned. I mean, inside the paper, if I remember correctly, he somehow doesn't explain how he discovered like the right restriction. Maybe he did a lot of different, like, try and errors, and then realize that you need to make the following restriction. So we need to first to restrict the size of support to be, then the support has to be finite. And of course, we need to further restrict that the Polyadic algebra is locally finite if like every element has a finite support. So that's the restriction he made inside his paper. If you do this, then in the other way around, every locally finite Polyadic algebra with infinite dimension means I don't restrict the size of variables. So you can still have an infinite set of variables. Then these kind of algebra actually is isomorphic to a function Polyadic algebra. So, and in a non-classical sense, we also have the following definitions. So, all right, so it's the mean of talk. And then for the rest of like 10 to 15 minutes, I will tell you how to use this framework to study first order algebraic implicative logics. Yeah. But the first order algebraic implicative logic has been developed by different logicians, Peterson Tilak, Carlson Pereva, and other different logicians. And then I think they summarize their results inside their book, Logic and Implications, published around like 2021. So, and it's actually the very end chapter of that book. So, and how to define algebraically implicative logics? There are like, of course, several equivalent definitions of this logic, and I give a somehow more syntactic way of defining this logic. And of course, I assume a little bit that people knows what is the basic definition of logic in this sense. Otherwise, I would have to explain everything here. Then that would be like a semester course in this direction. And actually, they really gave a semester's course about how to study the implicative family of logic at Charles University, like around like 3 or 4 years ago. So to really dig into the details, that will spend you a lot of time. So, and And logic is algebraically implicated if we say there is a binary connective, either it's primitive or it's definable, and a set of equations like E in one variable, such that my logic, because I think logic as a kind of consequence relation, so I collect like what happens, what I think should exist inside logic. So these are like the usual actions you think that I would like to see inside logic. So, and the most special, like the most specific axiom is this axiom. So because if we want to characterize a logic through set of equations in one variable, then we think syntactically we should see it inside logic. So we put it into axiom. Yes?
I'm sorry,
Yes.
on the right-hand side of the alg definition,
Yeah.
the last one?
Yes.
Yeah, the last
Yeah, you said it was most distinctive.
Yes.
P is a proposition, on the right-hand side I see a set.
So the right hand side will be a set, and then that means you need to be like interdefinable, interderivable, not dividable.
I see, and so the elements of this set are biconditionals, I see.
This,
Yeah.
yes.
But what are the relations among the biconditionals such that you get a proposition on the right as well as the left?
What's the relation of the biconditional? Let me see here if I type so, if I write something incorrect. If you want to use, if you don't have bicondition, then you just put like mu to v,
Pair to-
and then nu to mu in the same set.
pair of
So-
I
So you
I think this
put,
is how they define it, no? How they
you
define
put
bicondition.
pair of like implications.
Yeah.
So you have mu imply nu,
Mm.
and you have nu imply nu, and you just put both things inside the set. That's all. And that's why how they interpret like bicondition. If you don't have like other logical connective like.
I see.
So because in bicondition now, I have to see the implication in both directions, right?
Mhm.
So I just put both like one direction here and one direction. I put into the same set, and then that's all.
Mm.
And that's like some kind of shorthand they write like inside the book.
Just a comment, maybe I'm wrong, but this reminds me the last two, like Leibniz's rule of equality, right?
Yes.
Yeah.
And there is some connection
Yeah,
between their framework, and then you are actually telling something the Leibniz hierarchy you can see, and they spend a lot of time like I don't know if people can see it. The blue part is actually their research around like 20 years research study. And the inner part, the black part is like typical Leibniz hierarchies you can see in abstract algebra logic. Then try to somehow connect everything with the usual Leibniz hierarchy. So actually you can also do like Leibniz congruence and then so on and so forth. Then you can build up the whole hierarchy. And this is the very beginning, like we know about abstract algebra logic. And here is the things we want to study today. And of course, there are a lot of different families happens here. And I think it deserves like the semester's supposed to introduce the whole framework. And
Right.
I won't ask for that. On another occasion.
sure. And so the following things is just standardized introduction to what happens inside the implicated families of logics. And then, of course, they want to study the battery semantics of abstract algebra logic. So if L is a logic, and I just write like mod L with a star as a class of reduced models of L. And why we want to study reduced models, there are a lot of different reasons. So, but as far as I know, it makes like the theory or the framework steeper. And if you don't want to study like reduced models, then things will be even more complicated. And I would say an algebra is an L algebra if actually it's an algebra of some of the models. I would say this is a matrix, and then some of the matrix, and then take the algebra parts and then just call it an L algebra. And of course, I should put the citation here because I type it too fast. So that's not, of course, not my work. That's their work, and then actually they call it second companion theorem. And you can, because we define something syntactically in the previous slides here, and how could you connect things together? And this is the convenience theorem. You can see it in the book, and actually it takes some time, but not super hard to understand what's going on. At least they can teach like undergraduate students. So I don't think that would be something very, very hard, but it takes time to explain what happens inside it. So yeah, and you want to, but for why people want to study algebraically implicated logics, because the matrix semantics actually depends on the set of like truth value or designated values, and sometimes. But if you want to really study algebraic logic, we just want to see what happens inside algebra. We don't want like extra matrices. If the F set can be like somehow get from the information you already have about the algebra logic, that will be super nice. And that's why they study algebraically implicated logic, because they push the limit of this like definition and see if I only have an algebra of my logic, and how much information can I like retrieve back through to the matrix semantics. So you would expect like F should be some kind of definable on it. Yes, so that's somehow the spirit of this definition. And so I would say an algebra, we say an L algebra, actually you can characterize through the following quasi-equations. And I think that's actually a like proposition inside your book. So you can actually axiomatically characterize the algebra inside algebraically implicated logics. And so you can expect that actually we will take this algebra as our value algebra inside the Polyadic algebra framework. So actually the whole framework inside the paper, inside Picozzi's paper, is not hard to understand, but hard to follow, because they have 4 different frameworks inside the paper, and you need to follow what's going on right now and what's going on later on, and then they will say, actually, okay, put into the general framework, we get the theorem, but wait, what's going on then? And that's the things you need to be careful. But okay, for algebraically implicated logic, we're still in the proposition level. And for Polyadic algebra, we can algebraize like non-classical predicate logic or non-classical first law logic, how to do that. And then we need to study the first order algebraically implicated logic. And actually, this definition can be even much like more general than algebraically implicated. So the original framework, they can define is weakly implicated logic, and I think that's the like main logic they contribute to abstract algebraic logic. And you can characterize the first order, the minimum part, the first order algebraically implicated logic through the following axioms. And then of course, like it includes inference rules. And these are like the usual axioms you can find in any, I would say, non-classical predicate logic. So for example, if you study relevant predicate logic, then they will also put something, but not everything inside their framework. So these are like, I think our basic understanding about practical logic here. So I will now explain what's going on here. And of course, then we would like to introduce what happens within the models, and then the model will be, of course, and the model will be just the usual sense you can see from the basic model theory course. Interpretation, you will need to pick up the domain, but right now, it depends on the structure because our bottom logic is in like non-classical logic, but our bottom logic can be determined by the set by an algebra. So I need to put the algebra inside the model. And for the classical model theory, because we always study with the algebra, so this take it as a like background information and wouldn't mention inside the usual model theoretic definition or usual model theoretic constructions. Yes, so the interpretation is defined as a usual way. And of course, then I have to somehow, for the completeness, okay, in a naive way of presentation, and I need to tell you that what happens within the evaluation in this way. But if you have like basic logic course, you will know that this is just the usual definition of evaluation, and nothing special happens within this definition. It's just like the usual way of defining evaluation here. And then we need to use our model to interpret what happens within the first order implicated logic. And the things different from the hard way is actually right now we really use soft according to Font's explanation, the soft way. So we use infimum and supremum to say we run through all the things through the evaluation. If the infimum and supremum does not exist, then I would just leave it there and then say the value is undefined. But we don't like to see this the situation happen. So say usually if you want to prove the theorem, you say, okay, let us take the structure to be safe because you take infimum and supremum and get it. Yes.
How is the order defined? I missed that somehow.
Yes, I hidden behind it. Actually, the order defined is like you need to have your filter, like matrix filter F first. But how could you get your filter is because you assume the existence of equation E. Then you say, okay, I take all the elements which satisfy the equation. I take it as a filter. Then I say if something, because right now in our language, I'm pretty sure that I have implication.
Yes.
So A implying B is in the filter. Then I will say A is less than equals to B.
But it's a pre-order, right?
Yes, it's just a pre-order.
So the inf and the superior is over this pre-order.
And they need to do more work, I have to say, but it's actually basically just a pre-order.
Okay.
Yeah, so that's why they make assumption that, okay, I want to get something, really get something, so I would say, okay, everything is defined for each V and then each evaluation, and then I always work in a some kind of safe structure to prove a more general theorem. So that's how they define the order in this framework. Yes. So then in the end, if we want to study how to use Polyadic algebra, because right now we have first order implicated, algebraically implicated law. Can we connect it? No, can we somehow study the algebraic structure of this logic? Yes, and then that would be I call it Polyadic L algebra with this kind of capital L. And of course, because inside Picozzi's framework, he studied like set of generalized quantifiers, so he doesn't restrict it. But right now we have only interest in the usual universal essential quantifiers. So restrict this thing to a set of quantifier with only two quantifiers inside it. And also we assume that our because we want to study first of all the algebraically implicated logic, so we assume that at least there exists a operation, a binary operation, which is an implication. And of course, you can have something else. And yes, so to put everything together, and then this is the long definition you can see here, and you want to use the axiom of Polyadic algebras, and where the axiom is at the very beginning of Pigotti's framework, and then the axioms of L algebras is actually just the axioms here. So I put it inside my framework, and in the end, you need to also write down what happens within the quantifier part, and because in a classical case, I don't think universal quantifier and essential quantifier is interdefinable, so I have to write out the definition for both cases. Yes, so that's the axioms you can see. And we want to prove this, we just do the same thing as Ramos did inside the paper. So what happens within the functional Polyadic L algebra in this case, and then all right, I rewrite everything. I say value algebra is the case, and then our essential and universal quantifier, I use generalized means and join, and then just as they do in this case. And here's like a small lemma, and the proof is not hard. You just see what happens in the inside their papers, and then the proof, you just rewrite everything, and it still works. So if you take the set of predicates generated by, you take set of predicates and you see what's the generated algebra of this set of predicates, and this will give you a functional Polyadic algebra indeed, and with the usual variable, and var is defined at the very beginning of the slice. Yes. So then you will see every functional Polyadic L algebra is actually a Polyadic L algebra. And so the thing you have to do is to verify all the axioms as you can see before. And we want to see what happens in the other way around. And we need also the same restrictions. So every locally finite Polyadic algebras, infinite dimension, and actually isomorphic functional Polyadic algebra. Then you use their general theorem, and you can get the functional Polyadic algebras, but you are not firmly sure what happens within the quantifier. So the things you need to check is, this is like some kind of generalized joint meet. Then I want to, no, this is some kind of things defined on a set of variables, set of elements that variables. And I want to show that these two things are actually generalized joint meet. Then I can get a functional Polyadic algebra. You can see in like previous slides, because we defined it as a generalized joint meet. And there are a lot of like detail how you can really check the proof, but like the sketch is not that hard, so they just want to produce an algebra and to make sure that this algebra is actually the functional Polyadic L algebra we want. So this is the whole thing happens here, and so you might ask, so what's new? And the new thing is, yes, actually inside, because in the Salibras papers, they don't have to restrict to Russell implicated logic. The whole things also work for algebraically implicated logic, and that's the new thing. But if you really follow what happens in the inside the paper patiently, then you can get a conclusion. But we want to also study what happens inside cylindric algebra. But I will face some difficulties, and this is the equality I can give based on this framework, because usually we also want to study first order logic with equality. But how could you define equality? Classically, of course, Ramos also does the equality framework in another paper. So there's another paper, a shorter one, and then it's like Polyadic algebra with equality. He defined what happens about equality, but if you want to do it in a non-classical way, and if you don't assume that you have a lattice redux, you are just in the implicated logic sense, then things will be something more tricky. And because we want to see what's the connection between polyadic algebra and then cylindric algebra, classically it has been done, of course. But for the main difference between cylindric and polyadic algebra is about substitution. And here, if you want to do the substitution in this sense, you need to take equality as a primitive operation. That's what I did in cylindric algebra. But how to do the classical cylindric algebra? It's not a easy things, and especially you need to have these logical connectives. But if I assume that I only have implication as a primitive logical connectives, then things will be even difficult. Yes. So, but do people really care about it? I have to say, if you check what happens within the latest book about restricted lattice theory, there's one book like restricted structure in algebra and logic, written by Francesco Poli, George McAuliffe, and Konstantin Tsanakis. At the very, very end of the book, the very last open problem about that book, I think that's the very last pages. And then they raise up the question, how to study non-classical cylindric algebra. They would like to see it in at least as an open problem. But if you really dig into detail and then realize that, oh, okay, what do you mean like non-classical equality in this sense? And you can write down some definition, but then you need to do the translation between polyadic algebra and cylindric algebra. And things will be more complicated, and then you might produce something formally true, but you couldn't like explain everything intuitively or to persuade logicians that this framework also makes sense for non-classical equality, especially for relevant logicians. They have more general understanding about equalities, and then if your framework doesn't fit their understanding of equality, then that wouldn't be a nice framework. So that's one of the things I want to do. And also, thanks to Alexander, he was there. So we've been discussed this topic. And of course, you can also connect it with category theory. And there are actually some works. So if you want to study the connection between the classical polyadic algebra and the hyperduct transfer work, there are already some work by Maruyama and then Bloomfield, if I pronounce his name correctly. And interestingly, actually they announced their results right here around BLAST 2022. And there are like 2 papers in this direction, and then they give you how to study triadic algebra in a categorical way, because they think, okay, if you want to do algebraization, why not we use like Topless or hyperduct framework, and then you can still see it as an algebra. Nobody would say algebra should be these things. And also, Alexander has already done some works about non-classical polyadic algebras. Then we would like to know how to also study it through like presentation of functors. And the very end work, of course, is the more recent study about polyadic algebras, because if you check out what happens within polyadic algebras and cylindric algebras, and then see like a total different presentation of it, and then some of the presentation will be based on relation algebras, and then of course there are still many different presentations, and then I would like to see what happens inside it. So there are still a lot of work like to be done, and I wanted to know more. And good. So that's the all things I present today. Thank you very much.
Thank you. there questions or comments?
I have a question because thank you for your talk. So at the beginning, you said you wanted kind of to relate the soft and the hard,
Yes,
right? So can you summarize that for me, what your conclusions on soft and hard are again?
and soft and hard is, this is functional polyadic algebra. And the soft part is because
Wait, so you're saying,
yes,
can you go back?
here,
So the functional polyadic algebra, that's the
Yeah.
hard thing.
that's the soft thing. Because I interpret the quantifier as a generalized join and meet.
But polyadic algebras do have kind of a modal operator for the quantifier. So I thought that's hard.
Yes, so that's polyadic algebra,
Yeah.
not the functional case. And that's why, that's how I say you connect them
So
together.
the functional ones are the soft.
Yes,
Right.
Yeah.
Okay. So every functional polyadic algebra.
yes. And also you can do other way wrong with
So soft is hard.
soft is hard and then but hard.
Hard is not soft.
Some hard is soft.
Just trying to, I just.
Not every hard is
To
soft.
find a
Small
way to
hard
remember
is-
your conclusions.
Yeah. And actually, Alexander and I, we've been checked like what's the terminology means, and actually Fong's really use soft with quotation mark and hard quotation mark inside his textbook. Of course, I think that's his own understanding about algebraization, predicate logic. And I don't think maybe it's not, I don't think it's a standardized terminology, but it's about like his more or less intuitive understanding about these two different people will always be confused. Like, yes, please.
Yeah, I have a question.
Yes, please.
Symbolic algebra somehow deals with the negation, complementation, right?
Yes.
So what be the role of adding, because this is completely positive, would it be much more complicated if you try to take care of the complementation and negation side?
Exactly. Because if I just assume the existence of implication, then I don't even say I have like constant language, nothing. Then I couldn't even tell you what's happened within the complement part of, and then equality, actually the equality itself is like equal or non-equal. So it's like a binary concept, but how could you do it?
Right.
Yes, and how could you do it in a non-classical case? That will be
Yeah.
tougher. And of course, if you say, okay, I have like bounded distributed lattice redox, then of course you have top and bottom, you have conjunction, you have disjunction, you like or join the meet, and then things still work. But if you want to put things to the most generalized case, and then that wouldn't, or the framework would be like the framework doesn't exist in this case. It might be possible because it might, it doesn't make sense to say what happens in non-classical equality because, okay, that's not equality, that's a different predicate. Okay, you can use your own explanation like in this way if you really want to artificially define an equality. And so, yes, but I would like to try and see what happens within this direction of research. Yes, please.
Just following up on Alex,
Yeah.
I must have just misunderstood. You said there's some overlap between the hard and soft
Yes.
interpretation.
Yeah.
Is the results more stronger than that? Like one is properly a subset of the other, properly contained in the other?
Within this logic framework,
Yeah.
soft one is actually definitely the hard one.
Okay.
But some of the hard one, because I need to make more restriction about the hard one. And if you do the restriction like locally finite and you infinite dimension, these technical restrictions, and then the hard one would be also the soft one.
I see. Okay.
Yeah.
They can be made to coincide.
If you
You're on
restrict,
the right
if you
restriction.
restrict yourself to only like locally finite cases, and I think there are like some logical explanation about locally finiteness, but I'm not an expert in this field, so I would leave like other people to explain. Yeah.
I wish I could help. Thank you. That was helpful.
Yes, and so that's some kind of interesting framework, and then I found this framework just randomly searching, and then it's actually related to the discussion with Peter we had this morning, because I want to find his notes on partially ordered algebra. So I check what happens within ResearchGate and academia .edu, and I scroll down and I realize, hey, what happens within this paper? And it's like non-classical Polyadic algebra. I never heard this before. What happens? Because he did it, so there might be something serious. He wouldn't do. I don't think he would did something totally nonsense. So I dig into the paper and realize, oh, actually the framework makes sense even in the more general cases, and that's why I give the talk today. Yes, so that's the whole story happens within the talk today.
There was a slide where you had a bold capital P. It was for the near the end. Yeah, this one here. This
here.
P is the
and P is bold capital B is. I should put everything because I introduced the language.
Yeah, it was at the beginning. Yes, P is for the propositional. No, wait, the relation symbols, right?
Yeah.
And
here is the theorem actually.
The theorem doesn't allow function symbols. That's
Exactly.
what I wanted to check because
Exactly
that's
the
what I
theorem.
remember. Yeah.
Inside the theorem, he ignored the existence of function symbols.
Yeah.
Say let's for temporary
Mm-hmm.
assume we don't have function symbol in our
Right.
language, and then we can show
Yes.
we can construct the examples here.
Uh-huh.
And then he wants to give you because he wants to give you actually an examples about non-classical function Polyadic algebra.
Yes,
But,
yes.
yeah. Otherwise, that would be just a theoretical framework, but without anti or specific examples. And I have to say, if you read what happens inside the article, like Homos wrote around 2000, he did some kind of survey, like his later career, and then explained why he just left the research of Polyadic algebra. And then one of the reasons he mentioned inside the article is that he thought the framework is quite satisfied, but he couldn't see like empty examples. So it's not somehow, my understanding is it's not fruitful enough for him. And of course, a lot of researchers did a lot of different works, but maybe all the works like don't attract him anymore. So that's how he explained what happened within this like Polyadic algebra research.
On the second last slide, there was some references. I had a question.
Second,
this one, the person for relation algebras. What is the name?
this one?
Yeah, the last one. The last one. What?
Oh, it's Sagi, and then it's inside a like
Sagi. I see.
It's inside a monograph, which somehow they summarize what happens within mostly symmetric algebra in recent years. And that's one of the paper. If you Google Polyadic algebra and then you want to see what's the most up-to-date presentation, you can easily find this paper. And then I think I put it here. So this
I see.
So this is actually symmetric algebra in a gray.
Okay.
And that's one of the chapters inside this paper.
And it's Daniela. Okay.
Yeah.
I didn't know it was within there.
Yes, and I didn't know it until like Alexander pointed out to me that, hey, we actually also did some research on this direction, and there'll be something more interesting if we can really dig into it.
So I was at Iowa State University in 1993.
Oh, really?
This is when I got to know Antonino Salibra because he was there, of course, and they were working on this lambda abstraction algebras, which you mentioned,
Yes.
and that's out of which some of these ideas came. And
I think that's this.
Yes, there.
Even though So the other side is like notorious
But this priest,
recently.
No, but recently, not
Yeah.
95.
Not 95, of course. So the paper, the quality of paper, I would say, is still high.
Oh, yeah.
But no guarantee for recent papers.
Well,
very nice.
Yes. So that's all the reference about today.
Yeah.
Okay, thank you.
Thank you very much. Let's thank the speaker again. And talk some more. Anybody who wants to hang out, but please
Another meeting.
stop the recording. Thank you.
see you around.
Tomorrow,
Yeah.
maybe tomorrow.
Tomorrow, yeah.